You need to be able to find the greatest common factor of a set of numbers. So what the greatest common factor is the biggest thing that fits into a set of numbers. So for example, if you had two numbers here, 46 and 84, you're looking for the biggest number that can fit into both of these numbers. So the best strategy probably to find greatest common factor is to just start dividing by prime numbers. You'll see why in a minute. So those are prime numbers. The only factors of them are 1 in itself. So it looks like for the first example we can divide both of these numbers by 2. If we divide 46 by 2, that will give us 23. If we divide 84 by 2, that will give us 42. Now we want to keep dividing these numbers that we end up with until we can't go any further. So what we mean by can't go any further is if you divided one of these and ended up with a decimal in the next line, right here kind of thing, then you would stop, and the numbers that you divided by, you would multiply all of those together, and that would be the greatest common factor. It turns out that 23 is a prime number, so you can't divide that any further by any number greater than 1. So the greatest common factor for this example is 2. So let's try another example. 138 and 198. So again, our strategy is to just start dividing by prime numbers. So let's start off with 2 because these both end in 8 and looks like I can divide by 2. So let's do that. So if I divide 138 by if I divide 138 by 2, it'll give me 69. And if I divide 198 by 2, that gives me 99. So I think I can go further with this. I think I can divide these numbers by maybe a 3, so let's try that. So if I divide 69 by 3, that gives us 23. If I divide 99 by 3, that will give me 33. So I would try to take this further if I could and keep dividing by prime numbers, but turns out that 23 is prime itself, so I can't go any further with that. If I divided 23 by some other number, I would end up with a decimal. So we take these two numbers, we multiply them together, and that gives me the greatest common factor. So 2 times 3 gives 6, so the greatest common factor is just 6. Let's check that this greatest common factor of 6 fits into 138 and 198. So let's try 138 divide 6. So that works. If I do 198, divide that by 6, that also works. You need to be able to find the least common multiple of a set of numbers. The least common multiple is the smallest number that a set of numbers can fit into. So let's take a look at an example. 28, 42, and 63. If we were to find the smallest number that this set of numbers can fit into, the best strategy probably is to start by finding the prime factorizations of each of these numbers. So the prime factorization for 28, you can split that up into 2 and 14. So 2 times 14 will give you 28. 2 can't be factored any further. 14 you can split up into 7 and 2. So that's as far as you can go. You can't divide 7 by anything further. And same thing with 2. Next, find the prime factorization for 42. So 42 you can split up into 6 and 7. And 6 you can split further up into 3 and 2. And 7 is as simple as it gets, because 7 is prime. Alright. And last, find the prime factorization of 63. So 63 you can split up into 7 and 9. 7 you can't split up any further, but 9 you can split up into 2 3s. So 7 times 3 times 3 will give you 63. So we have our prime factorizations here. 28 you can write as 2 squared times 7. 42 you can write as 2 times 3 times 7. And 63 you can write as 3 squared times 7. So the secret why we were doing these prime factorizations for each of these numbers is so that we can find the least common multiple. So let's see how that works. So we go through each of these prime factorizations here, and we pluck out all of the unique factors. So we have a 2, we've got a 3, and we've got a 7. The lowest common multiple will contain these unique terms that we identified above. So it'll have a 2, a 3, and a 7. So next we go through and identify the highest power of each of these terms. So the highest power for the 2 is 2 squared. So we write 2 squared. The highest power for the 3 is 3 squared. So we write a squared there. And the highest power for the 7, all of these are just 7 to the 1. So 7 to the 1, which is just 7. So 2 squared is 4, 3 squared is 9, and 7 to the 1 is just 7. So 4 times 7 times 9 will give you 252. You'll need to be able to categorize real numbers. So given an arbitrary real number, say 1.25, you'll have to say whether it's natural, whole, an integer, rational, or irrational number. So starting from the center, just to refresh your memory, natural numbers are these like Sesame Street counting numbers. Whole numbers include 0, and then you could keep counting forever. Integers include negative numbers, so like that, they include 0, and you could count forever towards the negative direction or towards the positive direction, as long as you like. Rational numbers are things like fractions, so it could be something like -3 over 2, could be 1/2, that kind of thing, 100 over 20, anything like that. They include decimals that terminate, and also decimals that appear to repeat. So if they don't appear to repeat, then it's not rational. So if it was 787878 repeating, that would be considered a rational number. Last, we have irrational numbers. These are numbers that don't, so decimals that don't repeat and don't terminate. So things like pi, things like the square root of 2, something like -1.2794776 doesn't appear to have a pattern. That's the idea. Let's have a look at a few examples. So 1/2, well, what is 1/2? It's not natural, it's not whole, it's not an integer, it's not irrational. This is a rational number. Another example, square root of 25. The square root of 25 you can simplify is just 5. So what number times itself is 25? It's 5. So 5 is, well, 5 is natural. 5 is also whole. It would be in there. 5 is also an integer. And 5 is rational. So 5 you could say is natural, whole, an integer, or a rational number. You couldn't say it was irrational though. That would be incorrect. So any one of these would be correct. Another example, square root of 2. If you take the square root of 2, this gives you something like this. Now it doesn't appear that the decimals repeat, and you could assume that these decimals would continue, but the calculator just doesn't have room to show all those digits. So it would be safe to assume that square root of 2 is an irrational number. Lastly, 5.2713. Now here's a decimal. It doesn't look like it repeats, but it terminates. So a decimal that terminates is a rational number.